So in talking about the different groups attached to benzene, we can have electron withdrawing groups, we can have electron donating groups, there's a push and pull between resonance and inductive electron withdrawal, and the outcome of the reactions also get affected. So the resonance electron donating groups overall would direct the reactions so that the products or our new substituted groups would end up in the ortho positions or the para more likely than others, whereas the electron withdrawing groups, if the reactions did happen, then they would direct to the meta position. And you can't really explain that without looking at resonance structures through the course of the reaction. So I'm going to show two reactions, a lot of resonance structures. They both start the same way, right? So take my phenol, add to the new strong electrophile. This would be a nitration reaction. If I do that, then I have a choice, right? So do I put the nitro group on the ortho position here, right? Or do I put my nitro group on the meta position, right? So at this point, they look about equal, right? So there's nothing really favoring one over the other. This is the slow step in the reaction. This is the highest energy barrier because we're breaking that aromaticity up. It's no longer an aromatic ring. Right now with this new group substitute on there, before we do the elimination, it's not aromatic, it's unstable. But just like in other reactions, if we have a carbocation, right, we can look at what's going to make that carbocation more stable, right? So the more stable carbocation intermediate, the faster that reaction is going to go. Right, this isn't so different than looking at an SN1 substitution, where we had something like a highly substituted carbon. We break off that leaving group and form a tertiary carbocation. All of those methyl carbon electron donating groups can push electrons in and make that a little bit more stable compared to primary carbocation, so if we try and do an SN1 substitution on this, we would make a primary carbocation, which is pretty unfavorable. There's not a lot there to help stabilize that. So then this reaction didn't so much happen because it's just too slow. It's too unfavorable for that to happen. If there's a competing reaction like an SN2, that would happen. So in trying to figure out these reactions, look at the hard step, look at forming an unstable intermediate, and if we can make forming that intermediate easier and faster and more stable, then it's going to work better, right? So in the simplest sense, what we're looking at is comparing the different resonance structures. And what might stand out right away is for phenol substituted in the ortho position, I've drawn 1, 2, 3, 4 resonance structures. For phenol substituted at the meta position, but what we're saying is less favorable, I've got 1, 2, 3, right? So the more stable resonance structures you have, the better the resonance electron sharing is. The more equal in energy those are, the better that resonance electron sharing is as well. Right? So I've done this. My first step, where I can share the electrons around the ring. One of the key steps here is 3. So see, the positive charge here is right next to the oxygen with the lone pair of electrons. While I've broken up aromaticity, I still have resonance sharing through with that oxygen atom, right? So those electrons can move down, form a double bond to the oxygen, right? So I have additional resonance here when I substitute in the ortho position compared to with the meta position, right? So I started off the same. I have a positive charge, but it's just in a different spot in the ring. Doesn't look like any big deal, but right, if I'm right here with my positive charge at ortho, I'm moving these electrons over, right? My positive charge moves over here. I can move it again, right? But I never get to this spot here where the positive charge is near the alcohol. right, these lone pairs of electrons can't really get involved in the resonance, right? So instead of being able to share almost all the way around the ring and then up to the oxygen, I can only share around these 5 atoms, right? So a positive charge and these 2 conjugated double bonds, good electron sharing there, but these lone pairs can't get involved in the resonance. So that means overall, this is a weaker, less stabilized system. So remember, again, we draw these as a shortcut to kind of understand resonance on paper, but really what we're saying is it's not as stabilized, right? So this intermediate is going to be a lot easier to make. It's going to be a kinetically faster reaction than this one. And so if that ortho position reacts faster than meta, right, that's going to dominate the reaction. So without drawing all these again for para ends up with a similar situation. If you do the nitration reaction at the para position, you end up with a similar resonance structure to this where the positive charge can share with the oxygen. So basically, it just has more resonance stabilization. So why ortho and para? Right, they have more resonance stabilization. And that's it.